right, as we get started, let's go and review some things we talked about the last couple of days. We've been working with angles and triangles and angles in triangles. And perhaps one of the most important things to keep in mind that is in any triangle class, the three angles will add up to a straight angle. Their sum will equal a straight angle. Good. Now, based on that proof, that was Theorem 11, based on that fact then, we said that an exterior angle of a triangle, finish the thought, Lana?
I remember the old thing.
What's the old thing?
It's greater than either opposite interior.
Good, and that's still true, right? An exterior angle is greater than either opposite interior angle, but...
It's equal to the sum of the opposite.
Good, it's equal to the sum of those two opposite interiors. So it's bigger than either of them, but it's equal to their sum. We also said that in any right triangle, the two acute angles are complementary to each other. We said if two triangles have two of their angles equal respectively, what must be true, Abby? If two angles of one triangle equal two angles of another, then the third angles will be equal. Or in two right triangles, if an acute angle of one equals an acute angle of the other, Adam? In two right triangles, if one acute angle in one triangle equals an acute angle in the other, Dylan? The other acute angles have to be equal to each other as well. We had also discussed different ways to prove triangles congruent now that we knew all these things about the angles of triangles. So open up a few more ways to prove triangles congruent. Michael?
HA.
Hypotenuse angle is a new one that we added.
SSA.
No, not side angle. Noah? Side angle, right? A couple more angles there. So side angle, something new that we introduced. There's another one that we kind of just broadened its meaning, Brandon. Leg angle, there we go. Leg can only mean one thing, but leg angle, right, had originally meant leg at adjacent acute angle equal to leg at adjacent acute angle. Well, now it could be leg at an opposite acute angle if we wanted it to. So we opened up a few more things there. We'd also said that if two triangles have their sides parallel, right side to left side and left side to right side, the angles are supplementary. But if the sides are perpendicular, right side to left side and left side to right side, the angles are supplementary. But then if the sides are parallel, right side to left side and left side to right side, the angles are supplementary. But if the sides are parallel, right side to right side and left side to left side, the angles are equal to each other. But if the sides are perpendicular, right side to right side and left side to left side, the angles are. But if the sides are perpendicular, left side to left side and right side to right side, then the angles are equal. Good. All right, go ahead and draw an isosceles triangle on your paper. Go and draw an isosceles triangle on your paper. Draw it however you feel like drawing it. Tall, skinny, short, flat, whatever. Draw an isosceles triangle. And let's call it ABC. And I think we've done something like this before, where we took the bisector of this base angle A and the bisector of the base angle B. We got them to intersect. Now, we did a little bit different. We also drew a line up here. We're going to leave off on that. I want you to draw those two bisectors and have them intersect at a point P. I'm going to go and number these angles 1, 2, 3, and 4. So we are given isosceles triangle ABC with AC equal to BC. And we're given that PA and PB bisect angle A and angle B, respectively. PA and PB bisect angle A and angle B, respectively. I then want to extend side AB. Tell you what, I'll let... Adam, do you want to extend through A or extend through B?
Extend through B.
Extend through B. All right, so we'll go and extend side AB through B to some point. Let's just call it D. I want to prove that no matter how you drew your isosceles triangle, the exterior angle, CBD, will always equal the angle formed between the two bisectors, angle P. No matter the isosceles triangle, If you bisect the base angles, the angle formed by the bisectors will always equal the exterior angle. Once you have that down 2 columns, statements, reasons. Go and get down your first statement and your first reason. And let's start with Abby. Thoughts, Abby?
Angle A is angle B.
Why?
Because in a triangle, angles opposite each other.
Good. Angle A and angle B are equal because angles, you said in a triangle. In a triangle, angles opposite equal sides are equal. Good, so I know that this angle A and this angle B are equal. I just realized my bisectors don't look too good. Oh well. Oh, we don't trust our eyes. That's a bisector right there, folks. Wow. That's really bad. Oh, whatever. Let's see. Noah, thoughts?
Angle 1 equals angle 2.
Okay.
And angle 3 equals
Okay, and angle 3 equals angle 4. Reason?
definition of angle.
Adam, thoughts?
Let's see, 1 equals 4, or 1, angle 1, angle 2, angle 3, and angle 4 are all equal?
They are?
Well, if angle A and angle B are equal, then, how would I say? If angle A and angle B are equal, then,
And they are, right? Angle A does equal angle B.
well, then, you wouldn't see. Then that means the sums are the same, so therefore, like, halves.
Oh, okay, so if I drew this angle here, and we'll call it, we'll call these angles 1 and 2, and I drew this here, and call this 3 and 4. If these two holes are equal, then these parts are equal and those parts are equal? So just because the holes are equal doesn't mean the pieces are equal, right? We can do this with lines as well, right? I take this line, and it's equal to that line. I chop it into these two pieces, and so they have to be the same as these two pieces. Is that,
So would you have to say that, would you have to say that angle 3 equals, angle 3 plus angle 4 equals angle B and stuff?
I could. I think you're on the right track. I just don't think maybe not quite executing here. Dylan, can you help him?
Substitute
Substitute what?
angle 1 and angle 2 for angle 3 and angle 4 for B.
I'll substitute the sums in. Well, if I did that, okay, so if I did that, we would have to say then that angle A equals angle 1 plus angle 2, and angle B equals angle 3 plus angle 4. Back to Adam, because this was your idea. What's the reason if we state this?
What's the reason?
Yeah, how do you know that angle A equals angle 1 plus angle 2? And that angle B equals angle 3 plus angle 4?
Sum is equal to or the whole is equal to the sum of all its parts.
Yeah, the whole is equal to the sum of all its parts. And then I suppose that, Dylan, your suggestion was to substitute 1 plus 2 in for A and 3 plus 4 in for B.
Yeah.
And you said substitute, so that makes that kind of easy, substitution. Any of you think of that during the sermon, by the way, in chapel today? When it talks about substitute, you put this in for that. I'm like, yeah, my geometry class was all about that. Brecken, do you want to build on this thought, or do you have another thought? Because your hand was up a minute ago. Did you have another direction you wanted to go with this, or is this kind of falling in line with what you were thinking?
Just thinking halves of equals are equal.
Okay, so halves of what equals?
A, B.
Halves of A and B. Do we have halves of A and B? Where?
Bisect.
Oh, that's true. Bisectors give
Equal angles.
equal angles, but they also give equal halves, right? Now, we could be working toward that, but remember I told you a while back, when you have an angle bisector, or bisector in general, if there's one thing being bisected, just say the two pieces are equal. But if there are two things being bisected, I encourage you to state, not that angle 1 equals angle 2, class, but that angle 1 and angle 2 are equal halves of, in this case, angle A. And we could say that angle 3 and angle 4 are equal halves of angle B. So as needed, you could do some cross out, you could do some erasing. Probably easier if you didn't have an eraser like this, just scribble out and rewrite. But this is going to be helpful because then we can say what Adam was trying to get to, right? Adam, going back now, if we know that 1 and 2 are halves of A, 3 and 4 are halves of B, and we know halves of equals are equals, then we can say what that you wanted to say, Adam.
Angle 1, angle 2 equal angle 3 equal angle 4.
Yeah, all 4 of these angles are all equal because halves of equals are equal. So that's where we were trying to go with that, but it predicated itself on stating that we had halves. Now, if we took what Dylan had kind of worked toward, getting 1 plus 2 equals 3 plus 4, we could do a substitution. We could get ourselves right back to this point anyway. This is going to get it done more efficiently. So this is where I wanted us to go with that. So despite what it looks like in my sketch, all 4 of those angles are all equal to each other. All right. So Michael's got some ideas. Remember what we're trying to prove here. We're ultimately trying to prove the exterior angle equals that angle at the top. Michael, what's your thought?
Can we state that angle 3 plus angle 4 plus angle CBD equals a straight angle?
Okay, sure. We could say that, because of course about a point on one side of a straight line is a straight angle, so we could say that angle 3 plus angle 4 plus angle CBD equals a straight angle. Again, I think I kind of just said it, but Michael, how would we word our reason here?
All angles about a point on one side of the straight line are equal.
All the angles about a point on one side of a straight line are equal? So all 3 of these angles are equal because they're all on one side of a straight line about a point?
Equals a straight angle.
Oh, so all the angles equal the straight angle.
Mm-hmm.
All the angles about a point on one side of a straight line equals a straight angle. So because these 3 angles are all about a point on one side of a straight line, they're all straight angles?
The sum.
The sum of all the angles. The sum of all the angles about a point on one side of a straight line equals a straight angle. There we go. That's our informal statement number 10. Hey, but you know what? That's what you got to do, right? When you're doing the proof without me, is look at what you've written and say, wait a second, does this read correctly? Or do I need to clarify it more? And so good, we got there. Now, I'm going to cut him off. Brandon, your hand was up. Were you by any chance thinking along the same lines as Michael, or is that vastly different from what you were thinking? Kind of along the same lines. Okay, so what's your thought? How can we use this straight angle that's right here to our benefit?
Well, I know what I'm supposed to get. I just don't know how to get there. So, angle 2 and angle 3 equal angle. So like angle 3 and 4 equals 1 and 2. So then you can substitute angle 2 and for angle 4. So angle 3 and angle 2 Will be supplementary.
Huh? Lana, do you have any thoughts? Or did we just work Michael through something that we're going to have to turn around and erase like we did a minute ago? No, Josh is like, no, please, no, not more erasing. Now, is that a hopeful no, or is that a no, don't erase it, I can use that?
No, it's not.
It's not a, I can use that. It's a just, I don't want to erase anymore. You're just thinking it. Okay, Adam?
I guess if you really want to, you could say that angle, I mean, that PA and PB equal.
We could, couldn't we? I mean, after all, PA and PB are opposite equal sides, couldn't we? Is that going to get me to getting a couple of angles equal here? Well, it could get these two angles equal, but we already know they're equal, so we're working our way towards sides. It wouldn't actually end up helping us, but it wouldn't be points off in a proof if you said it. It'd be like in the middle of a murder case, randomly interjecting, and by the way, this guy shops at Publix. Okay, that may be true, but that has no weight or bearing on the case, unless, of course, some evidence was found, like, DNA evidence was found on a pack of cheese or something. Aha! I knew it! Whatever, I don't know. It's probably no weight or bearing on the proof. Brecken?
So, angle 3 and angle 4 plus angle CBD equals the straight angle.
Right, that's what he
And
said.
Angle 4 is equal to angle 2 because the halves of equals are equal.
Right, that's what we said there. Are you just going to restate everything? I'm just picking.
I mean, sort of, but no. So, if, like, the 4 is equal to the 2.
It is?
A triangle. All
What
the angles in
triangle?
a triangle adds up to a straight angle.
What triangle are you talking about?
The PAB.
PAB, okay.
So, see, angle 4 plus angle 3 equals angle 2 plus angle 3. So
what should I write down for number 6?
I think angle CBD equals angle P, right? You could
I think you're doing a lot in your head. It needs to come out on paper. I think your thought is all there. Michael, come back and help him now, because he's thinking it through properly, but he's not got it. Actually, Abby's got her hand up. Abby?
I was doing that, but you could say that angle 2 plus angle 3 plus, can we label that angle 5?
Right here?
No, CBD.
Here. I guess.
Let's leave it off for CBD.
But then we have to label it here, and
Abby.
but it's fine. We can label it 5. That's fine. Or y'all can leave it as CBD.
Angle 2 plus angle 3 plus angle 5 equals a straight angle.
That's what your brother said.
2.
Oh, 2 plus angle 3 plus angle 5. Oh, angle 2 plus angle 3 plus angle 5. Sorry, equals a straight angle. Okay, now what did she do there, class? Substituted, right? In place of the 4, she kept the 3, she kept the 5. She just put a 2 in place of the 4. That's a substitution. That kind of sounds like something Brecken was trying to suggest. Okay. Brecken, you kind of build on this? Adam?
Wait, so could you say that angle 3 plus angle 4 plus angle 5 equals a straight angle?
I already did.
Since a triangle equals a straight angle, could you say that angle 2 and angle 3 have parts? So you could, use substitution to say that.
This is the second time somebody said the angles of a triangle add up to a straight angle, but no one's ever put anything in the proof about it. Is there something we could put in the proof, Brecken, about the angles of a triangle equaling a straight angle?
Angle 2 plus angle 3 plus angle P equals a straight angle.
Okay, so we could say that because what was the reason again?
All angles in a triangle equal a straight angle.
All angles in a triangle equal a straight angle?
The sum of all
Oh,
the angles in a triangle.
the sum of all angles in a triangle equals a straight angle. Okay. We hadn't actually said that yet. Yeah, people kept hinting around at it, but they hadn't actually gotten around to putting it in the proof yet. So then what's the next thought, maybe? I kept trying to come back to Michael. Michael, go ahead.
State that angle CBD or angle 5 equals angle P.
How?
We've already stated that 1 and 2 and 3 and 4 are all equal. So
Right.
just subtract it
From what?
from Okay. Mine's going a whole different direction.
Brandon?
Well, first we have to say angle 3 plus angle 4 plus angle CBD equals angle 2 plus angle 3 plus angle.
All right, he's not an angle 5 guy, so he doesn't fall in line with the 5 thing. He said, say that angle 3 plus angle 4 plus angle CBD equals.
Angle 2 plus angle 3 plus angle.
Right.
All straight angles are equal.
Okay, so number 8, all straight angles are equal. Okay, so you kind of just like
Yes.
flipped right through that. You said, I don't need that. Is that what Abby said?
Yes.
I don't know, he's got something against Abby here. He's like, he doesn't like her angle 5 that she came up with.
No.
And he just like takes her statements like, I don't need that.
No.
All right. And now, Michael, now coming back to what you said,
State that.
because 3 is here, and we know that 2 and 4 are equal from earlier,
State that angle CBD equals angle 2.
we're ready to go ahead and say now that angle CBD equals P. The key was, Michael, we needed to have 2 sides equal to each other before we could subtract away. Does that make sense? And the reason for number 9 is subtraction axiom. The subtraction axiom. And there's our proof.
That was way too long.
That's a little way too long.
All right, so let me kind of recap the proof here since we went a lot of different directions here. Clang, equal sides, equal angles. Bisectors, clang, equal halves. They're all equal to each other. We have a straight angle here. We have a straight angle here. All straight angles are equal. So this sum equals that sum. But I can subtract away the 3 from both sums, a 4 and a 2 which are equal from both sums, leaving me with equal remainders, CBD and P. And so there we go. Could have done it in 8 steps. We took 9 because we had an extra step in there for number 6. But that's fine. Questions on this?
I didn't do 6.
Here's what Abby was thinking. She wanted to set it up this way, where she could subtract the 2's and the 3's off. But here's the deal. I could subtract the 4 and the 2 because they are equal. So I didn't have to replace that. I could just subtract the equals off. I didn't have to substitute, make them look the same before I took them. Does that make sense? Okay. All right, questions. Questions on this? Doing a lot with angles, right? A lot with angles, some bisected angles. In fact, if we did some numbers with these, let's suppose, class, this was a 50-degree, let's go with a different number. Let's go with an easier number. Let's say it's a 40-degree angle. How many degrees are left? 140. And if you split it evenly, how many would be in each of these? 70, correct? Now, how big would this exterior angle have to be? 110. The sum of these or the supplement. Now, if I bisected right here, how big is each piece? 35. If I bisect here, how big is each piece? 35. So how many degrees, if we've used 70 down here, how many degrees up here?
10.
Right? That's kind of the math application of the same thing, though, right? And all it is using bisectors, equal angles, and straight angle, and putting it all together. All right, clear desk except for a clean sheet of paper and a pencil. Clean sheet of paper and a pencil. Everything else away. Calculator. You might want a calculator. You don't need a calculator, but you're welcome to have one. Makes you feel good. Without talking, clean sheet of paper, pencil, optional calculator. First and last name at the top of your paper along with today's date, which is 10/14/22. 10/14/22, today's date. 10/14/22, and this is quiz 12. Quiz 12. 10/14/22 is today's date. All right, go and take one, pass the rest back. All right, take a look at the quiz together very quickly. Numbers 1 through 8, you have completion. Figure out what word, words, phrase, whatever needs to go in the blank, put it there. Obviously, shorthand's acceptable. number 9 and number 10, I've given you one angle in 9, I've given you one angle in 10. I need the other two angles of 9 and the other two angles of 10. So number 9 will have 2 answers, and number 10 will have 2 answers. All right, you may begin. Keep your work covered using the quiz copy as a cover sheet. Once you finish, turn the paper over and stick quietly. About another minute or so to be finishing up. Everyone take out your notebooks if you would please. Turn to the Theorems Corollaries section. Theorems Corollaries section of your notebook. And there is one last way to prove triangles congruent that we have not gotten to yet. How many already knew that? As you looked at that post here, you're like, yeah, we've got all that one, that one, that one, that one, that one. We're missing that one. So we're going to add our last one to the list, Theorem 12. And it's a rare theorem that deals only with right triangles. That's not always the case, but this one is. Theorem 12 says this: two right triangles are congruent. Two right triangles are congruent if the hypotenuse, that's hype, H-Y-P, if the hypotenuse and a leg of one triangle. Two right triangles are congruent if the hypotenuse and a leg of one triangle. Two right triangles are congruent if the hypotenuse and a leg of one triangle are equal you don't even have to say respectively in this case, are equal to the hypotenuse and a leg of the other. Are equal to it the hypotenuse and a leg of the other. Two right triangles are congruent if the hypotenuse and leg of one triangle are equal to the hypotenuse. And I used to saying respectively. I even had it written. I'm like, wait, you don't need to say that logically. Are equal to the hypotenuse and a leg of the other. Are equal to the hypotenuse and a leg of the other. And anyone want to guess the abbreviation we'll use here? HL, hypotenuse leg. So this is our hypotenuse-leg theorem. Once you have that written down, turn to the proofs of theorems, corollaries. Proofs of theorems and corollaries. And at the top of a new sheet of paper, put Theorem 12, HL. Theorem 12, HL. And then if you would go and draw a couple of right triangles that to the best of your ability appear to be congruent. Not sure that I did a particularly good job of that, but whatever. All right, draw a couple of right triangles that sort of look congruent-y. Mine, not so much. The second one definitely looks bigger. We don't trust our eyes, but I'm going to try to help out a little bit. Let me shave a little bit off this. That looks a little bit more like it. Okay. Let's call the one ABC. And let's call the other XYZ. We are given right triangle ABC with right angle A. And we're given right triangle XYZ with right angle X. And the theorem states that these two triangles are going to be congruent if the hypotenuse and a leg, let's go with this one, are equal to the hypotenuse and a leg of the other. So we'll also be given that BC equals YZ, there's the hypotenuse is equal, and AC equals XZ, and there are the legs equal. We want to prove, of course, that if the hypotenuses and legs are equal, that the triangles have to be congruent. So prove the triangle ABC is congruent to triangle XYZ. Once you have that down, two columns, statements and reasons. Get down your first statement and your first reason. Now, what ways do I already have to get right triangles congruent? Dylan?
Side over side.
Well, right triangles.
Oh, 8,
Leg, and
Leg angle. There's one more. Hypotenuse angle. Now realize this is going to be easier than the others because the others have three things, right? Side, angle, side, 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 angle, side, angle, side, angle, angle. These only have two things in each of them. And the premise is they only work if you have right triangles, but I'm given the right triangles. I don't even have to go out of my way to prove they are. I was given that they were. So I might definitely want to cash in on one of these methods. Let's see, I've already got legs equal, and I've already got hypotenuse equal. So I don't know there's really an advantage either way, right? I mean, kind of whatever, right? Thoughts? It's true, and we could say that angle A equals angle X. Would that give us leg angle or hypotenuse angle, class?
No.
Two right triangles are congruent if a leg and an acute angle of the one. Two right triangles are congruent if the hypotenuse of one and an acute angle. Yeah, so the angle, that's important to remember, and I'm actually glad you brought it up. The angle does not refer to the right angle, and that's specifically why we have separate methods that are easier, because it already accounts for the right angles being equal. So no, that's it. You know, I'm glad you mentioned it at least, because other students in the past have had that same thought. I'm sure other people in the room have that same thought. So either I got to get these two legs equal, or I got to get these two angles equal, or I got to get these two angles equal. Adam?
Never mind, that's not it.
What?
Can we do leg?
If I could get AB and XZ to be or XY to be equal, how might we get AB and XY to be equal? Yeah, kind of at the same point, right? It's like there's not a whole lot. I mean, there's plenty in the given. It seems like there should be so much to go off of, but there's actually not as much, which suggests either the use of auxiliary lines or move through space. In this case, it's going to be a move through space. Here's what we're going to do. I can't necessarily take this and place it on top, though, because although you could obviously line up these sides, because I don't know that these angles are equal, how do I know that these sides would line up? I know that this side would have to line up because these angles are equal, but I don't know that the ends would. Do you see the problem we've got? So here's what we're going to do. Instead of placing it on top, I'm going to flip it and place it next to. So I'm going to take C, and I'm going to put it right here. I'm going to drop the A, I'm going to line it up somewhere along here. I'm going to allow B to be somewhere over here, so it kind of looks like that. Now, truth be told though, class, A isn't just going to end up falling somewhere along here, is it? Where's A going to fall? Exactly on X, isn't it? And then because of the right angle, it's going to push a right angle off this way also, isn't it? So A is going to fall exactly here, and coming off exactly perpendicular will be this. So A will end up being here, B will end up being here, C, of course, will end up being there. So let's go and talk through, because again, the wording is the hard part on this. Place triangle ABC alongside triangle XYZ so that C falls on Z. Again, you can always line up 2 points with each other. A falls along XZ, because for now that's all we can specify. And B falls on the opposite side of XZ from Y. Place triangle ABC alongside triangle XYZ so that C falls on Z, A falls along XZ, and B falls on the opposite side of XZ from Y. And our reason here will simply be that a geometric figure may be freely moved through space without any change in form or size. Or move through space. But again, because AC and XZ are equal, if they line up with each other and one pair of endpoints coincide, class, the other endpoints still in good have to coincide because anyone? How do we know? You said A had to fall exactly on X. Why? What? Because AC equals XZ, and what's the definition of equal line segments, class? Endpoints can be made to coincide. So yes, A coincides with X based on the definition of equal line segments. Now here's a thought for you. We have a right angle at A. We have a right angle at X. Normally, we get right angles, class, if we are given what kind of lines? Perpendicular lines. But you realize if you have right angles, you must have perpendicular lines as well. Number 4, I'm going to specify that XY is perpendicular to XZ. I'm going to specify that BA is perpendicular to, now it would be AC, but AC and XZ are in the same position now, correct? They are coinciding with each other. So therefore BA is also perpendicular to XZ. Does that make sense? Based on the definition of perpendicular lines. I have right angles, therefore I have perpendicular lines. But since A coincides with X, it looks like, class, two lines are perpendicular to the same line. But how many perpendiculars can you have to a line at a point? 1. So if XY is perpendicular at this point, and if BA is perpendicular at that point, then this must be one straight line, correct? So therefore, BAY is a straight line. Or you could say BA and Y lie in a straight line. I'm just going to say BAY is a straight line. But you can also say BA and Y lie in a straight line because only one perpendicular may be drawn to a line at a point in the line. In this case, it's the end point, but we still have, A is still a point in that line. X, A, whatever you want to call it, it's the same point, right? A and X is a point in the line. You can only have one perpendicular. We have two perpendiculars at that point, therefore we don't have two, it's one continuous line. And if that's true, I have one line here, BC or BZ. I have one line here, BY, and I have one line here, ZY or CY, correct? If we have 3 straight lines, we have a triangle. So therefore, we could say that BYZ or BYC is a triangle based on the definition of a triangle. BYZ, or you could call it BYC, because Z and C are the same point, is a triangle. And remember the two hypotenuses were equal? Well, that's these two lines now. And in a triangle, class, they are equal. And if in a triangle, two sides are equal, opposite angles have to be equal. So angle B must equal angle Y. Because in a triangle, angles opposite equal sides are equal. Go back to the original two triangles for a moment then. I have hypotenuses equal. Now I have angles equal. So I have Congruent triangles by hypotenuse angle. Or you could say I've got legs equal and I have angles equal. So class, I have congruent triangles by leg angle. So number 8, they're congruent. And you can choose. You can either put leg angle or you can put hypotenuse angle. Either will work. Number 8, and we're done with the proof. The triangles are congruent either by hypotenuse angle or by leg angle. Fit it on there. Fit it on the front if you can. I mean, squeeze it in there. Are you leaving blank lines between statements?
Yeah.
Don't do that. There's not room. Especially as the proofs get longer, you won't have room. Don't leave blank lines. Squeeze it in there. All right, so a little bit of a weirder proof, right? But not totally unconventional. I mean, we did something similar in Theorem 4 where we placed one alongside the other. It was underneath, if I remember correctly, and got our isosceles triangle that way. Kind of unusual, but there we go. So that adds hypotenuse leg to the lineup. So moving forward for right triangles, leg angle, hypotenuse angle, hypotenuse leg. A fourth way we can use to prove right triangles congruent. Yes, sir?
What was the reason to the
Congruency, class?
Leg angle.
Leg angle or hypotenuse angle. You can put either one you want. So if you'd rather say la, then you can say that. If you want to say ha, then you can say that. It just depends on what you feel like, what the mood you're in. All right, questions on this? Or if you want to reverse it, do angle hypotenuse. Ah, you do that too. All right, anyway. Abby just got it. Sometimes the jokes are so dumb they take a minute, don't they?
Oh.
Anyway, questions. All right, for homework this evening. You're going to copy from corollary 12.1 to corollary 14-2. So that includes a few corollaries and a couple of theorems. They're on pages 84 to 86. Pages 84 to 86. Get corollary 12.1, theorem 13, corollary 13.1, theorem 14, corollary 14.1, corollary 14.2. Get those statements copied in your notebook. So from pages 84 to 86. So corollary 12.1 all the way until you get to corollary 14.2. You're going to copy all those. They're kind of like yellowish, brownish shaded box in your book, a beige colored box, whatever color you want to call that, whatever it is. You're going to copy all those things into your notebook. We'll talk about all of those in our next lesson. We'll also look at your quizzes in our next lesson. All right, when the bell rings, you will be dismissed.